Okay. Can I start? Yeah. I wait for a few minutes before hitting this. Okay, clock's ticking. There were three remarks I wanted to make at the end of previous lecture, in part inspired by Yogesh, I think, but asked some questions at the end. So first thing was, yeah, I had this somewhere in the background, so I pulled it up. These are slides of, as you can see, James Lee from Simons some time ago. He had this nice slide that shows for diffusions why you don't have all these avatars, so to speak, of log Sobolev inequalities. There's just like one log Sobolev inequality. It's because of the chain rule that the usual calculus gradient satisfies. So that's my first remark, gradient of f with the chain rule. So Dirichlet form is defined, in any of these ways. So I think I took this definition, or that definition doesn't matter. But the point is, the Dirichlet form we had for log Sobolev, which was this, and the last one is for the modified EF log F, right? These are all the same because of what we have for the usual gradient. But for discrete gradient, it's too fragile. They're not equivalent. But one of the first proofs I showed that said log Sobolev is at most modified log Sobolev or twice or whatever, was the proof that said this is at least, some factor 1/2 or 1/4 of that. So there's at least an inequality here. Yeah. Exactly, yeah. For certain functions, yeah, so it's not equality, but you can make work with inequalities sometimes. That's been my experience in terms of what I call discrete calculus. You can get away with inequalities sometimes up to constants. And I'll briefly mention this notion of discrete curvature. There's like half a dozen notions, and they all coincide in the continuous framework. So people like Villani, Sturm, and Lot Villani, Sturm, and Rob McCann, people in optimal transport, developed very nice notions of so-called displacement convexity to capture Ricci curvature. And there's several things that are all the same, or at least it's clear what implies what. And people wanted to develop analogs in the discrete spaces, and each of those statements, if there are 3 or 4 that are equivalent, you can take each one as a definition, and you get something, which is interesting or not, but they're not necessarily equivalent. So there's now like half a dozen notion of discrete curvature. S.T. Yao and the collaborators in differential geometry developed one. There's a paper called Li Yao, Li-Yao, Y-A-U-S-T Yao, inequality for graphs. So there's a famous Li Yao inequality, again, for diffusions on manifold and so on. And dimension and curvature plays a role. Dimension in discrete, people tend to think is like the degree locally of every vertex. The question is, what is curvature? And they made up one definition by using the fact that gradient of square root f satisfies a certain inequality. Again, this chain rule is not robust, but for gradient of square root f, you can make something work. And they developed a certain curvature type things there. So that's sort of the story. My sense, having worked on such things for a number of years, is you should identify what problem you want to solve, what relation between diameter and eigenvalues or what, and then use the appropriate notion. That should probably work. There is no no unified decurvature of a graph or anything like that. Yeah. Here I think it is. I just wanted to say, but it could be more general. More general. Yeah, it could be with other. But what I was speaking about earlier is with respect to measure on a graph and so on, discrete measures, where we defined a gradient in a different way. Yeah. Mm-hmm. Yes. Yeah, in the graph case, we define the gradient of a function locally by taking average over the function value over the neighbors and so on. And I was saying that discrete gradient doesn't satisfy the integration by parts formulas as nicely. And so various complications arise. Second thing I wanted to address is so one question Yogesh asked was, I think maybe I oversold the modified log-Sobolev inequality, saying it gives the correct bounds for certain Markov chains and so on. And he was saying, so maybe the log-Sobolev is not relevant or interesting anymore for discrete Markov chains. But that's not quite true. There's still two things that are good about the log-Sobolev versus MLSI. And that is, I had mentioned, so again, LSI, I use this rho as the constant, and MLSI alpha, right? The definition was overall F and so on, and this one was so the two things are, in terms of advantages, so 1 over rho up to some constant is a lower bound still on this tau 2. I'll say what I meant. Earlier I didn't define tau 2. Up to this log 1 over smallest entry in the plus some log, maybe 1 over epsilon, whatever, right? The epsilon Fabio took as 1/4, for example. If you ignore the, up to this factor, it captures tau 2. By tau 2, what did I mean? I meant of the density. So this is, so the appropriate norm is, again, as usual, we take worst case, starting state, and then what you're measuring is, suppose mu t is the distribution having started at x of where you are at time y, then with respect to pi, take square of this in, again, L2 pi sense, and square root of that. You want this to be less than epsilon. Okay, so it's minimum t, t0 such that t bigger than t0 implies this is less than. That's what I meant by tau 2 epsilon. If I took the one norm here, right, this would cancel with that and you get the total variation. So tau 1 would be total variation. I mean, up to some factor 2, sometimes it's called chi-square or something, I think, conversion. So this mixing time, which is in general tau TV, which is the same as tau 1, up to a factor of 2, is smaller than tau 2. And the point is inverse log Sobolev gives a lower bound for this larger mixing time. Whereas we don't have that with lambda or alpha. I mean, with lambda, it would be weaker, right? Because we had rho less than alpha and lambda, so 1 over rho is the larger than the other ones. Sorry? Sum over y, sorry. You're right. Sorry, yeah. Okay, so this is my, you like mu t 2 pi. Okay? So there's a square and then the square root. Thank you. Sum over 1. Okay, so that's one thing. So it's good in terms of lower bound. The second thing is there's a nice technique or trick called comparison argument. So if you have two different Markov chains with the same stationary distribution, and you know the spectral gap or log Sobolev of 1, and you would like to use that and get a bound for the other one. As you can imagine, if you could simulate one chain using moves of the other one, you think you should be able to get bounds using the one that's simulating, since you know the spectral gap. Or that works. You know, Diaconis and Salafkos wrote a paper a number of years ago that works for both this and lambda, but not for this. There's a simple Cauchy-Schwarz argument. You know, basically you take a move of, say, the known chain, and then describe a path using moves of the unknown chain. And that's where the Cauchy-Schwarz comes. For the Dirichlet form EF log F, it's not true. Yeah, it doesn't work.
Is the Markov chain irreducible?
Yes.
And finite countable?
Finite, irreducible, and even reversible.
Reversible?
Yes, reversible, and we want to know, yeah, it means in the long run, the transition of going from one to the other is the same as the other way around. And what we are interested in is the rate of approach to equilibrium. How quickly does it get?
So the rate of convergence is
Exactly. Yes. And these functional constants describe how quickly. One in total variation, another in relative entropy, and so on. Okay, so those are some advantages still, right? The comparison most notably. But of course, the disadvantage is that there are examples where this is worse than that. This is of the same order as that, but yeah.
When you were describing relative entropy, you said you could use any convex function, not just relative entropy.
Yeah.
Would you expect the same rate of convergence in all these cases? Is there some universality there? Or?
I don't know. So, as I mentioned in the first few slides. Yeah, the question was, so I motivated some of the study by saying if you look at convergence to equilibrium in terms of how variance is decaying, then this spectral gap is useful. If you look at decay of relative entropy, some other constant is useful. And I said, somewhat flippantly, that you can take probably some other convex functional and so on. When we wrote this paper, Bob Koff and I, we realized the two examples we had, this transpositions and the slice of were precisely the two that Gao and Quastel wrote a short paper about, without developing the theory or anything. So then we said, okay, we have to do something. And so we took a P norm that we measured rather than L2 or anything, LP distance between P and P1 and 2 in a certain sense, and as P approached 1, it captured the relative entropy. For P equals to 2, it captured lambda. And we gave a uniform bound for those examples in terms of P. But other than that, yeah, I haven't experimented with. Yeah, these are the standard distances, but they could very well be. One other thing we haven't explored is, so symmetry is not really needed in terms of, reversibility is not needed in terms of studying entropy decay. In principle, you could study entropy decay in a non-reversible, because relative entropy is not symmetric and so on. The Dirichlet form EFF automatically symmetrizes, turns out. Even if P is not reversible, it loses that when you look. It's equivalent to looking at P plus P reversal over 2 or something. Whereas the modified log-Sobolev doesn't do that, but I don't know examples where people have exploited. Okay, I want to go back to one other point. So as time was running out, I skimmed over this convexity aspect of the functional R. So, I described this certainly, right? I said this is going to be important. So RAB in the modified log-Sobolev was A minus B times log A minus log B. And then it has this property, R of the averages, the most average of the R's. Now, notice that here it's the same measure, mu I of x mu I. Okay? But what if I have one average here and a different average there? In a general decomposition theorem, that could be the situation I'm in. Because this is the ith piece, omega I, omega j. So the average here could be different from average. And in the projection chain, this is omega I, and this is omega j. And here I had f bar I, here I had f bar j, right? And somehow this, the R of f bar I, comma f bar j, I want to expand and take the average outside. So that requires I put it on somehow on a joint distribution, find a coupling or something. In the case of this symmetry group and transpositions, there's a lot of structure. So what happens here is, so in principle it should have been f of x, f of y, or log f of y, whatever. But I can write y as Sij of x, because there's a perfect matching between these two. If I have a permutation here, this is x. So this x corresponded to having x sub t be k, and here I have y, and y in the tth position I have L. Because in position t, I fixed card k in one place and card L. That's what gave me the partition. But there is a perfect matching between these, because if I do the kth and the lth card swap, that's exactly when I go from one part to another. If I swap any other cards and leave the kth card in the tth position, I stay here. Similarly with what's in the teeth. So the only way I cross a part is when I swap what's in position. So, but there's a perfect matching. So this measure, the step is easy in this case. What I want to say is here, I'm looking at R of f bar t of k, f bar t of L. This is an average over the kth piece. This is an average over L, as in what's in L. So I would like to take the average out. And here I say, there's a natural bijection between this and that. And that's precisely by swapping. Remember, the little s was swapping k and L. So that's, so when I go, so I want to go to the general decomposition lemma that, nicer than what we had tried doing 15 years ago, but was done in a nicer way by Hermann Sales earlier this year. And the key point was to focus on a coupling between pieces, two different pieces, and using that to leverage convexity. Yeah, since we ran out of time, that part I skipped. But So that once we write it as, one I can write as x, and rather than calling it y, I can write it as skl of x. So that lets me take, so the measure now is mu k of x, and this is also mu k of skl of x. But this is all the same. It's 1 over n minus 1 factorial or whatever, same measures I can apply. So it's kosher to apply that, the Jensen's. Okay, so ignore that if it was a bit technical. I wanted to mention that. And so this gives the n log n for the shuffle, and I just wanted to say the same thing, of course, works for spectral gap, but it's off by a factor of 2 or 4. The correct spectral gap bound was identified in this little book by Diaconis, but I think it's the work of Diaconis Shashahani. 2 over n minus. Okay. Moving on. So that was like a super classical, quite nice example. You have n factorial permutations. At any point of time, you have a permutation, a deck of n cards, and the move was transpose 2 cards. Life is much complicated, much more complicated, and we cannot do anything like that as far as we know. And this toyish problem hasn't seen optimal analysis, embarrassingly. There's good news and bad news. So what is the state space? The state space is what we teach in high school or undergraduate, depending on which district you belong to. Rather than n factorial permutations, look at the nth Catalan number many Catalan structures. Each one is a set of n balanced parentheses. So why n is 5 here, I have no idea. Anyway, so 3, it should have been 3, but it corresponds to the 5th Catalan number or something. So 3 left and 3 right. There are 5 ways of doing that. Right? We all know that the total number of ways is the same as ballot sequences, right? This is n ones and zeros, but the number of ones read left to right is always at least as many as number of zeros. What I describe as Y2K problem in Florida, Bush, Gore. Gore is leading all the way through the night, and at the end they tie. Right? How many ways? That's the nth Catalan number. Now, that's the state space. The chain is you pick a left and a right and swap. If we did just that, right, without any hassles, without any constraint, that would be 2n choose n. Because if I didn't care for the Catalan aspect, so let me say it again. I cannot take any left, any right and swap. For example, the first left, I can never swap with anything because that's already invalid. So the chain is pick any left, any right. If it gives you a valid, then accept it, otherwise reject. So now I never paid attention to the rate at which I do this or the transition probabilities. Because I thought, okay, it didn't really make much difference. So I was using 1 over n squared as the probability. With probability 1 over n, you pick a left, 1 over n, you pick a right. If it's valid, accept, otherwise reject. For that one, the best we know is n squared log n, as opposed to n log n for the card shuffles. Okay? Mixing time. We believe it's still n log n. Simulations, Yuval Perez had students implement it and study. So the rejection happens, if you visualize in terms of these ones and zeros, you have a path like this that starts at ground 0, and I don't know if I had enough. The problem is, if you flip this up step, this 1, this left parenthesis, if you swapped for right parenthesis here, right, then rather than going up, you're going to go first down, and then you continue this. So you continue one up, and then down, one up, two down, and so on. So here it's fine. So in general, it's some band like that. But you can imagine, if your level was like this, when you swapped, if you go down, you go too far down. So you'll be rejecting, right? So there's a constraint that penalizes you. But in terms of simulations, it quickly goes above the sea level. The sea level is only, when you try to go below the sea level, is when you reject. Well, we cannot prove that. And going back to my comment about I never paid attention to what probabilities I used to switch. So there's this major result that happened the last year that I mentioned for the basis exchange walk of any MATROID and so on. Turns out these paths, or these balanced paths, can be seen as basis of a certain MATROID called Catalan MATROID. What we did in this work was prove some negative correlation property and show that they form a balanced MATROID. And then from a previous decomposition theorem, we got log Sobolev and spectral gap are both at least this. Okay, that's how we managed. But I thought this was like a sledgehammer for a simple problem. I never thought. But it turned out, if you remove a left parenthesis uniformly, but then when you replace it with a right, you take proportional to allowed choices, rather than you don't do 1 over n. If there are only 3 choices allowable, you take one of those with 1/3. If you do that walk, that's the one that has nice properties. There's some completely log concave polynomial, etc., etc. Using some algebra machinery, they showed n log n.
You were rejecting order n rejection rate because you proved
Before, yeah. Here the rejection is much less. Yeah. Here you don't waste time. But I thought there was always some constants and some. But if I try to compare to that, I lose a factor of n and I don't get anything back. So this is still an open question for this, sort of not smart 1 over n chain. Can you prove n log n? If I throw out the Catalan restriction and I say, I give you n1s, n0s, forget the sea level, then you're inside this box, this diamond, right? Because these are n1s and those are n0s. These are zeros. Any path is in between these. This is the n slice of the 2n dimensional cube that we already analyzed. There we know n log n. And if I put this saying don't go below this, stay only above, we don't know. For the vanilla transitions. For the modified transition, now there is a very general result that gives. And what I meant by this many challenges is, Stanley has this little book of 214 realizations of the nth Catalan number. And there's a famous open problem of Aldous for, 25, 30 years.
Itself is like 1 over n to the 3/2.
Cn?
Cn itself is like 1 over n to the 3/2.
Cn is
According to
in the denominator, it's like 4 to the n over n to 3/2. Because 2n choose n is like 2 to the 2n over root n. And so Cn, which is 1 over n plus 1 times 2n choose n, is like that. So it's an n to 3/2 proportion of all possible or whatever. Yeah, so maybe in the open problem session I can mention a couple of other very nice ones, including Aldous' n to 3/2 relaxation conjecture. That's still open, wide open. It's, the best known bound is like n to the 4 or something terrible for triangulations of a regular polygon. Okay, so in tomorrow's lecture, I'll talk more about this, but I wanted to mention what it is that I will talk about. And also, I already used this M word, MATROID, which people usually freeze up when matroids are introduced. And the second thing that happens is people say, well, here is an example, and they talk about graphical matroid, which is nice and very familiar and friendly, and then they don't talk about anything else. But matroid is a generalization of a graph and a vector space, in a sense. These are the axioms. Okay, so you have some ground set, let's call it E. There are several equivalent axioms, so here I'm choosing one, and that is identify a collection of what are known as independent sets. Okay, these scripti is to think of as independent sets. These are like independent sets of vectors in a vector space. The empty set should belong to the collection, and it's downward closed in the Boolean lattice, meaning if you have a set that belongs to the collection, then any subset of that should belong to the collection. Again, true, right? If you have a collection of vectors that are independent, you take a few vectors out of the collection, that's still independent, right? The third one is an important one, augment. There are equivalent ways to talk about the third one, like exchange axiom and so on. If you have two and one is larger than the other, then there's something from the larger collection you can add to the smaller one and keep it independent. These are the axioms. Any system, any collection of sets over any set E that satisfies this is a matroid. Then with these you can prove that all the maximally independent collections have the same cardinality and so on. This is the like in finite vector spaces, that's the dimension of the vector space, right? Here we call it the rank. The maximum independence of bases, they're called like in vector space. And the rank is the cardinality of any of them, R. For any two bases, from these, it's not hard to show that there is a sequence of exchanges of elements that takes you from one basis to any other basis. So the typical example everybody gives is spanning trees of a connected graph. So E, in that case, is the set of edges, and dependence or independence. Independence is if in your collection you don't create a cycle. You can have just empty set, a single edge, two edges which don't give you a cycle, and so on. So the largest independent set will then be a spanning tree, where the graph is connected. Okay? And you can go from any spanning tree to any other by this familiar basis exchange walk. Take an edge that's not in the spanning tree, add it, it creates a cycle, remove another. So that case was well understood. It was part of a balanced matroid case, that how fast it was mixing and so on. So this general conjecture of 30-some years is that for every matroid, this particular random walk is mixing in polynomial time in N and R. Now it's a theorem. And in fact, the one bound using modified log Sobolev inequality that they identified is R log N, where R is the rank, N is the size of the ground set. And so Nima Anari showed me a proof a few months ago. So he and his collaborators first got a result in terms of spectral gap that didn't give quite R log N because of this log pi min versus log pi min, right? So they had a slightly worse one. And then there's this other group. They mentioned this group, Mary Krein, Hengu, and Georgios Musa, that got the modified log Sobolev constant. They showed 1 over R. So the same bound for spectral gap, Poincare inequality of 1 over R, was what Nima Anari, Shaya Noves Garan, and Cynthia Vincent got. But Nima since showed me a different proof, which is more in terms of a strong stationary time and stopping time. It still uses the entropy decay, but then does something else rather than bounding these functional inequalities. And it's R log R is the bound that he can. I don't think they posted it yet. He said they found something slightly more general, and they're looking for other applications besides this. But for now, this is the one. So again, I said it already. So PB sub x, this is the basis exchange walk. Ignore the homogeneous, strongly log concave for now. Think of pi as uniform distribution on the basis of matroid. They can do something stronger for other distribution. Remove an element uniformly. Here is the important thing. We're not adding again uniformly. Here adding with probability proportional to the measure of S union I. Meaning how many valid things are there that you can add this to. So in terms of this Catalan walk, this is the probability that would be different. That's 1 over n, this would be different. This is like 1 over however many allowed. Okay? So if it was this, this is not allowed with anything, so that you don't replace with this. But if it's this, there may be one other like that. Yeah, so tomorrow I'll mention a little bit more about this result. Okay? So you saw the list of things. I was hoping to do the decomposition also in part 1, but I'll try and do at least as much as I can do about these two. So this is very similar to what we saw in the symmetric group with transposition, but it's a more general theorem. And I think this still will have application because this way of formulating came up in February this year. Okay, what I'll show. We had something 15 years ago that saw some applications and so on, but it did not give it did not state the result for modified log Sobolev. It only stated for log Sobolev and spectral gap. So you do as before, you partition the state space like on this board into a bunch of parts and introduce a projection chain. Okay, the way to think of projection chain, so remember in the projection chain we think of each part as a single vertex and we identify p hat ij. Right? And how to define that? Well, there's a natural way. So the way to look at it is think of pi bar I, p bar ij. Rather than this transition, define p bar ij so that this is equal to the total flow between those two parts, which is x in omega I, y in omega j. This is bundling all the flow between these two parts. It's reversible, so there's no direction to that, right? Bundle that, and you want to capture that in defining p bar. If you define it this way, then it's easy to see it's reversible with respect to this pi bar of I, where pi bar naturally is the measure of this part, which is just sum of everybody in that. X in omega I. Okay? Very natural projection chain. Restriction is also natural. Okay, this part is easy to see, it's reversible, blah, blah. Restriction is even easier. Restriction means if you try to leave the set, ignore that transition. And adjust the diagonal so that you have a Markov kernel. Okay? Restriction. Pi xy is just pxy. It's just restricted to xy, both belonging to omega I. So suppressing the exit moves, because those are captured in the projection. This is general, very general. Now here is the key thing. This is what we did in a slightly ad hoc / somewhat of a hack in my paper with Jerome and Eric Vigoda and June Besson many years ago. We had all the elements, and they kindly, so in this paper, and Herman Sales kindly acknowledged that actually for log Sobolev and lambda, it's implicit in our work. this paper. But the key point is that they do it for all three in a uniform way in 2 pages. So you define a coupling between the ith and jth piece, as I alluded to earlier. Okay, you can have any coupling that you want. What do I mean by coupling? Coupling means the joint distribution between the ith and jth pieces with marginal, the appropriate marginals. The left marginal should be for the measure of the ith piece, right for the right. We had, remember, pi I. One marginal should be pi I, the other marginal pi j. Okay? It turns out how good a coupling is. So you can define this for any coupling. So the art to this doing scientifically will be in coming up with a good kappa ij in your application. And they call the quality of a coupling can be measured by this chi, for quality, I guess, by this. So what is this? So this is one, the way I think about it is, look at pi bar of I, p bar ij. That's this bundled total flow between the ith and jth pieces, okay? That's the total amount, and pi x, p x, y for individual states x and y is the weight that particular edge is carrying. Like if if that's too little compared to this heavy load, that's too much, because you want the minimum to be as large as possible. And kappa is, this is like the fractional amount that you distribute to ij. In terms of mass transport, there's a total of pi I here, total of pi j. Along a particular xy, you take a fraction. So the total amount of x, total amount, you see, I didn't write down the definition of a coupling, but if I sum this over all y in Sj, it should give me mu I of x. If I sum this over all x in omega I, it should give me mu j of y. That's what I mean. Okay. So it is whatever it is, but the theorem is, or lemma, then that the entropy constant or modified log Sobolev of the original chain is minimum of this fraction of projectional versus the worst of the pieces. We did something like this for these two other constants, but in the end our theorem had a result that said alpha of p is or lambda of p is at least product of these two. So somehow any theorem should use both these, because as I said this morning, if you expect the original chain to mix fast, you certainly expect each piece to have good mixing. Also, hopping over the pieces should be fast. So it's certainly capturing that, but it's not somehow uniformly.
Alpha of P what?
Sorry?
What is alpha of
Yeah, alpha of P is this constant. Alpha of P measures
the entropy?
Entropy decay rate. Yes. So there's this relative entropy of the chain relative to stationary distribution. It measures that you decay at this rate compared to the initial.
So there is a bound on.
Yeah, so on the entropy decay rate for a big chain in terms of these pieces of the smaller chains.
Depends on chi.
Also, yes, absolutely. Depends on chi. There's some easy lower bounds you can get on chi. For example, you can say because kappa ij is a coupling, it's trivially at most pi j of y or pi I of x and so on. And so you can have some cancellations and you get some bounds, yeah. There's some bounds like that mentioned. Okay, but so I was going to do the proof, or I actually do something in a bad way. This is, I don't want to insult people, but back in the day when we had transparencies, we had people like me who would print their paper, copy onto the transparency, and then slowly go line by line. I have the Hermann Salles paper on my computer. It's just a one-page proof of this. It's just like the proof I went through. The key is to replace the projection entropy term by the origin, by the Dirichlet form, and then expand it using convexity. And there we had a bijection. Instead, they use this coupling kappa ij to do that. That's the only difference. They use the kappa ij to make use of convexity of this functional R of AB. So it's the same idea. You start with entropy, write it as by the chain rule for entropy, right? Expectation of conditional entropy plus entropy of expectation. For each one you have, for the restriction chains you get these guys for free, and the projection one you use this coupling to make it work. That's the high level idea. Can I move on? I just wanted to mention. So the decomposition theorems are of this type. What you don't have here is, whereas we had in the symmetric Rupas, we could do this average over different ways of partitioning the state space. We didn't do it just once, and that, if you do it only once, you get only n squared log n, it turns out. So for Sn, it's important to do it. So in general, you don't necessarily expect like an optimal tight bound, unless it's like a discrete cube, or unless it's in the cases when chi is 1, because you have like a perfect coupling. In the paper here, what we observed was that for balanced matroids, in many cases, if you have a fractional matching rather than a perfect matching between the ith and jth piece, that's sufficient, because we use that fractional matching to construct some coupling. Whereas these guys, abstract it out even more in a nicer way and say, here is something you can take home. And they had some applications of this for what they call stochastic covering property that generalize both balanced matroids and so-called strongly Rayleigh measures and so on. So it's a nice paper. I recommend reading. Okay. This is still fashionable, mass transport, so much that even machine learning people are now talking about Wasserstein and mass transport. I want to mention briefly to talk about connection to the last topic, modified log Sobolev and concentration of measure, sub-Gaussian tails. Okay, what is the connection, or how many? There's a classical argument called Herbst argument that's used for log Sobolev to Gaussian tails. And we didn't have a nice way to do that. Again, the Hermann Salles paper did that. But we had a result, my student Marcus Samara and I, of a similar flavor in 2005, using a different idea, using an inequality that's from Bobkov and Goetze. Okay, so I want to mention that. Kantorovich metric.
Is it a distance function?
Is indeed. So okay. So for simplicity, for the present context, let me assume I have a graph and I have two probability measures on the graph. Why a graph? Take any metric space, so I need a metric and then probability measures.
So depending on gamma.
Indeed, and the best gamma is what you need.
Oh,
yeah. So W1 for Wasserstein, although my Russian colleagues correct me and say, why should it be Wasserstein? It should be Kantorovich. So, but this W is stuck. 1, because it's an L1 type thing. Infimum is over all coupling, joint distributions with marginals mu and nu. The expected distance in that. So you have a metric space that tells you distance between x and y, and then gamma is the amount of mass you're taking from x to y. Proportion. Okay? In the, for us in the finite dimensional case, this is just a linear program. Here are the variables. The constraints are in this, linear constraints. The total amount of mass taken from mu, given to nu, etc. Right? And this is a linear view. So Kantorovich, identified this dual, which is E mu f minus E nu f in a sense, because the first term is like expectation of f, second is like expectation with respect to nu, right? Over what f? The top formulation has distance d. If you just look at this, where is the distance? That's hidden in lip of G, Lipschitz. So over f that are Lipschitz. Lipschitz constant 1 with respect to distance. Okay? So this is an easy, actually this student, Marcus Sammer, he complained to me when I told him this. He came back and said, this is not the duo. And so it turns out you can do this for any cost function Cxy. To get this version, you must use that this is actually, this cost function is a distance, as in triangle inequality and symmetry. Otherwise you get f mu plus g nu subject to fx plus gy at most dxy. And then you have to, using distance property, you show g is minus f. In case I make trouble for you, I warn you, okay. All right. So here is a nice result of Borkar-Goetze, and this is a connection to sub-Gaussian concentration. So far I just defined W1 for you, which most of you probably knew. So what's nice on manifolds and Ricci curvature and so on, and in terms of what Villani, Sturm, those people did was, is W2. This is not linear, so this distance you square and then take the square root over the couplings. It's convex and it has much nicer, stronger properties. But in discrete, W2 is out the window. It's useless, it's not good. There are versions of W2 that are good. Okay, so this is our usual relative entropy. And what Borkar-Goetze observed is that if you want to bound sort of a log moment generating function of random variables, so if you want to bound e to the tf in terms of e to the expectation of e to the tf in terms of e t squared over 2, right? Over Lipschitz f, so that you can then do the usual Chebyshev argument or whatever and get a bound on deviation from expectation, right? That's sub-Gaussian, depending on this C. This is equivalent to a so-called transport entropy inequality. Transport because of this W1, entropy because of relative entropy. Such an inequality with W2 was something that's also known as Talleyrand's inequality, and Talleyrand used that to prove some nice results about concentration of measure. What these guys observed is that actually this is equivalent to this W1 version of transport entropy. Okay? I'm not going to show you the proof. In my student's Sammer's thesis, he wrote the details for the discrete case and so on. And it's a nice proof. It's not, one direction uses the duality I mentioned earlier, right? Because here you have Lipschitz F here, so that duality comes in one of the directions. The other direction uses Young's inequality and things like that. It's not. There was follow-up of this. I'll mention in what way. So what my student and I did was basically mimicked an argument Felix Otto and Cedric Villani had. So they showed log Sobolev inequality, our friend Rho there, implies Talleyrand's inequality with W2. Okay?
You can speak, right? When you knew
which is tight. You mean?
Yeah.
Right. So okay, is this achieved? Yeah, there's some properties we prove in terms of what can we say about, you know, the tightness and things like that. Yeah. I mean, we know some things, but not too much. But yeah. Especially using the dual formulation. So at that time, in 2005, I was trying to develop what is a discrete Ricci and so on. And so I was interested in somehow deriving something like what they had done. Turned out the natural analog in discrete was modified log Sobolev implies this inequality. So it's not, we start with a weaker hypothesis, not log Sobolev, but modified log Sobolev, and we have a weaker conclusion. You can show, because W1 square is smaller than W2 square, this is a weaker inequality. By the way, another way to get a feel for this is, if your distance is 0, 1 valued, W1 is nothing but total variation between the two. So this is our good old Pinsker inequality, total variation square, okay? This is a more general version of that. Okay, so we had some motivation to study that version, but, right, so our result was that. Now you may ask, if I want to show modified log Sobolev implies this sub-Gaussian inequality, transport entropy inequality, the transport entropy has no kernel, no Markov chain. So which Markov kernel do I use upstairs, modified log? The short answer is you use the best one you can, subject to something. So there is, because Lipschitzness is involved, it turns out, so here is the theorem. L is our usual, right? P minus I. So you can use any P, but you need some condition that sum of distance squared times this Laplacian, the at most one. Okay. Then this is our modified log Sobolev. It implies if this is alpha, this or 2 alpha, same. Of course, in general, it may not be tight and so on, but this is one way of getting concentration of measure, sub-Gaussian type state inequality starting from modified log Sobolev. I'm going to run out of time, but I'll just show the statement Herman and Saleh's proof, which is very similar but slightly different. And the proof is they use the classical Herbst argument, which somehow Borkar and I missed. And it's nice that they. Both proofs are short, and both use a certain, take the derivative and argue about the growth of, you look at this inequality as saying this minus that is greater than or equal to 0 or less than or equal to 0, and say at time t equals infinity, they're both equal, and the growth of one is faster than the other. So at start t equals 0, where you want the inequality, must be, the one that is going faster must have started smaller. That's kind of the idea in the Otto-Villani proof. So maybe I'll just take 2 minutes to say that. I won't show you that. I'll share the slides, and tomorrow morning I can go quickly over, but our proof is, as I said, so you want to prove this is at most 1 over alpha times relative entropy. 0 is because at time 0, that's what I put. And then I evolve nu according to the Markov kernel. Okay, so, and we prove something about the derivatives, that this W guy's derivative is faster than the other one. Okay, and at time t equals infinity, both are 0 because nu t is equal to pi. Also, so both Wasserstein and relative entropy, they're both 0 at time equals infinity. The derivative one is faster than the other, so at time 0, this must have been smaller than the other one. And that's this statement. Okay, that's sort of high-level idea. Okay, this is a comment. And the theorem of theirs is similar, Herman Saleh's. What they say is, take any P reversible Markov generator, then you have this sub-Gaussian statement. Okay, deviation by A is A squared, alpha is modified. You see this V or nu of F is this constant. This is almost like my sigma d square Lxy at most 1 type statement, right? You have the P kernel here. Rather than, so there's is a finer assumption because I assumed F was Lipschitz, so I can always bound this by d square xy. But they're assuming something weaker in a sense. It's for any F, if you can control this quadratic variation, then you get some. So again, it's a nice way to package, but the end result is similar without assuming Lipschitz. So tomorrow morning I can start with the proof of this and then move on to the basis exchange. Happy to answer questions. question.
You control over the variance.
Yes, yeah, with respect to this Markov kernel. It's a local variation, right? So that's another way to look at these constants.
So what do you want to call it? Gaussian?
Oh, this I want to call this exponential tail is one. Probability that you're certain distance away from the mean or probability you're so many standard deviations away is dropping like e to minus the square. Yeah. Sub because alpha is some, not the optimal constant as in Gaussian. Again, this is a general statement. Once you identify, you can cook up P, and if you control this and manage to bound alpha of P, then you have. Okay.
So P has to be reversible with respect to.
No question? Everything good? Okay, thanks.